If you have any questions, do never feel shy. Yes, because
Can you put the last equation that we wrote?
yeah, I'm just waiting for people to finish this board because it's right after this one.
It's after that.
It's down. Okay. Anybody wants this board? Nope. Okay. Here's your last two questions. In particular, I can put them in matrix form pretty easily. So, why this is useful? Why it was easier than Newton? We have to think about that. First of all, I want to ask you something. Is this bracket equal 0?
No.
Anybody agrees that this bracket for any mass should equal 0? Anybody agrees? Anybody doesn't agree? Do you guys have any suggestions for why this is not equal 0? This is indeed not 0, okay? First of all. Why? Because we are in the framework of analytical mechanics, where we don't account for constraint forces. This is indeed correct. It's Newton's second law, F equals ma. If you could account here for all the forces, including constraint forces, okay? But if you neglect constraint forces, if you ignore them, you cannot say the applied loads only equals mass times acceleration. Of course not, okay? This is one thing. So, this is one thing why it was easier, but there is more. By doing this dot product, it allows you to focus only on the acting motions, on the directions along which there is motion. For this guy, it wasn't moving in the y direction. We simply ignore anything here in the y direction, right? By this dot product, you dot with what? With the virtual displacement, and by definition, the virtual displacement is the admissible motion only. So, what do you mean by dot product? Dot product means that we're taking the component in the direction of this guy, right? So we're taking the component of the equation of motion in the direction of the useful motion, okay? We simply ignore anything perpendicular to the motion, okay? Yes, Ken?
I have a question. If M1 is very small, that we can ignore M1, can we still use that equation?
If M1,
Yeah, M1 is very small. If we want to ignore M1, I will still use that equation.
yeah, that's fine. You can still use it then with M1. Any question? Okay? So this is the principle of virtual work. It allows you to focus on the useful part of the equation of motion. It's simply, we are rewriting down. Remember, this was the equation of motion. F equals ma, or this bracket equals 0, accounting for all forces. So we say, no, don't take all the equation of motion. Focus only on the useful part by dotting with the admissible displacement. Now, when you focus on the useful part, the unuseful forces will simply be ignored, right? Because they are workless. The constraint forces dotted with this virtual displacement force is 0, okay? So we're focusing on the useful part of the equation of motion.
But the second thing does not relate to that Fi is not equal to Fi minus this is not equal to 0. This is an additional effect that we are dotting it with DRI, so all the component of the non-useful things, they go out.
This is why we were able to ignore the constraint forces.
Yeah, that could be an explanation.
Okay, we're gonna make it a bit more easier. Okay, right there. So again, I'll start with summation I1 to N mi ri dot dotted with dri equals 0. And remember that ri, the position of any particle, is simply a function of all the q's, right? All your q's, configuration coordinates, degrees of freedom. Okay? X and theta in our example. So can you tell me please what is DRI from here? What's that? Can you tell me?
Extra times theta.
It's what?
Extra times theta.
Yeah, I just want to make it general. So this R is a function of Q1 up
Partial
to
R by
Yeah.
partial Q1 into
So you're gonna do
dQ1.
it's partial R, right?
No,
Partial Q1
dQ1.
dQ1. In general, it's partial any R with any J, dQj, and I'm going to do that until Qn. Right? Differentiate with all the coordinates, d coordinates. Any question about that? So if you want to write it in a succinct form, we're summing over J from 1 to little n, number of degrees of freedom, partial your R, partial with any Qj, dQj. Okay? I'm gonna put this here. So now I have two sums, and I'm gonna get this sum out. So sum J equals 1 to little n. This guy as is. Throughout our course, I'm going to use I as a counter for the number of particles or bodies, and J as a counter for the degrees of freedom. Okay? So this guy now is here. So dotted with partial Ri, partial Qj. And now this is dQj. This is equal to 0. Any question? Any question? So this is what? This is as if I'm saying we have some complicated term multiplying dq1 or dx now, for example, plus the summation, something multiplying dq2, which is d theta, plus something multiplying dq3 if you have a third degree of freedom, and so and so. So what do you infer from that? Because this is valid for all dq's, right? What do you infer from that?
All equations individual zeros.
This guy is 0, right? For all j. So summation I equals 1 to n. Fi minus mi ri double dot dotted with. This is 0 for all j. So it's as if you do it for j equal 1, this guy, you get the equation for the x displacement. Do it for j equals 2, you get it for the theta equation. If you have third degree of freedom, do it for j equals 3 and so and so. What's this guy? So